Welcome back to Math on Catalyst University. My name is Kevin Tokoph. Please make sure to like this video and subscribe to the channel for future videos and notifications. In the previous few videos, we've actually proved L'Hopital's rule, and then we've used it to solve three examples for L'Hopital's rule where we have indeterminate form of a limit. And we've generally seen limits in the form 0 over 0, infinity over infinity, but in these two videos what we're going to do is we're going to see other kinds of indeterminate forms, and we'll see that we actually have to use some fairly complicated substitutions in order to solve the limit analytically. In this video, we're going to look at the limit as x goes to infinity for e to the x plus x to the 1 over x power. Now, this is not going to be a limit where you're going to be able to put it explicitly in a 0 over 0 form or infinity over infinity. In fact, we have another kind of indeterminate form that we're going to add to our list, and that's something in the form infinity to the 0 power. Now, we've learned in previous coursework in college and high school that anything to the 0 power is 1, but not necessarily. If something goes to infinity in the argument but it's raised to the 0 power, it may not be 1. In fact, it's not in this case. Alright, so if we plug in infinity, we'll show it's an indeterminate form. E to the infinity plus infinity, all this in the argument is infinity, but it's raised to the 1 over infinity power or 0 power. So we have infinity to the 0, this is indeterminate form. Now generally when we have something in usually the 1 to the infinity power or infinity to the 0 power, we usually have to do something slick like make a substitution. So what we're going to do is we're going to say that we're going to make a variable called z. And z is going to be equal to basically everything in this limit. So z is going to be equal to e to the x plus x all raised to the 1 over x power. Okay, that's going to be z. And what we're going to do is we're going to take the natural log of z. So here's where we start evaluating. The natural log of z, okay, we need to now take the natural log of everything else that's in this function. Okay, so the natural log of z is the limit as x goes to infinity of the natural log of e to the x plus x all raised to the 1 over x power. Now, why did we do that? Well, the reason that we did that is because logarithm laws state that if you have a log, any kind of log, and you have an exponent on the argument, you can actually pull that exponent out in front of the log. So, this equals the limit as x goes to infinity of 1 over x times natural log of e to the x over x. And because I have this thing times a 1 over x, the x can effectively be a denominator. So, I have the limit as x goes to infinity for natural log of e to the x plus x all divided by x. And now that I have this form right here, I now have an explicit infinity over infinity, because if I plug in infinity, the numerator is infinity and obviously the denominator is. So now I can apply L'Hopital's rule as before. So if I apply L'Hopital's rule, let's take the derivative of the numerator. So let's take the derivative of this natural log. The derivative of ln of e to the x plus x, okay, the natural log part of the derivative is 1 over e to the x plus x, but we now have to take the derivative of the inside function. So derivative of e to the x plus x is just e to the x plus 1. And what's the derivative of the denominator x with respect to x? 1. Now let's do this. Since we have a denominator effectively here, let's just pull this under. And so our limit now is going to be coming down here. Limit as x goes to infinity of e to the x plus 1, that's our effective numerator, divided by e to the x plus x. All right? And that's the limit as x goes to infinity. Now again, if we just plug in infinity, we still have indeterminate form because this is in the form infinity over infinity. So what do? We take L'Hopital's rule and do it another time. So take the derivative of e to the x plus 1. That's just e to the x. All right? What's the derivative of e to the x plus x with respect to x? Well, that's e to the x plus 1. Now we're still in indeterminate form because if we plug in infinity, we have, again, infinity over infinity. So guess what? We do L'Hopital's rule once again. The derivative of e to the x is e to the x. The derivative of e to the x plus 1 is e to the x. And both of these e to the x's now cancel, and so we just have 1. That's our limit, because now we don't even have to evaluate x, this is just 1. But be very careful. the value of this limit is not 1. Because, watch what happens. This whole thing, this 1, is actually equal to originally natural log of z. So, come back down here. The natural log of z is 1. Alright, so I come down here, and I know that ln of z is 1. I want to find out what z is. So, I have to take e and raise e to the power of both sides of this equation. So e to the ln of z, that's just z, because e and natural log are inverse functions, so they cancel. So effectively z is equal to e to the first power, which is just e. So this limit as x goes to infinity of e to the x plus x, all raised to the 1 over x power, this is just e. Alright? Now this is obviously not the definition of e because it has an e in it. To actually have the definition of e, we don't want to have e in this. So what we're going to do in this part of the video now is we're going to use L'Hopital's rule again, and we're going to demonstrate this limit right here, that this is e. Okay? And here's how we're going to do it. We're going to use these log laws that we had in the previous video, but I'm going to explicitly write them here. So if we have a function f of x, if e is to the f of x power and we take the natural log of that, all we're left with is f of x. And we can also use this form e to the ln of f of x. Both of these are equal to the original function f of x. Alright? Now this right here, this is the definition of e. The limit as x goes to infinity of the quantity 1 plus 1 over x all raised to the x power. If you evaluate this limit, it ought to be e, because this is the definition of e. Alright, so here's what we're going to do. We are going to use some log laws, as in these up here, to rewrite this and try to get it in indeterminate form. Alright, so what I'm going to do is I'm going to take this limit and take the natural log of it, but I don't want to change the value of the limit, so I take e to all of this. Because remember, e and natural log are inverse functions, so they cancel each other. So doing this, I don't change the value of this limit. But I do something really interesting. Whenever I take the natural log of a limit, that's the same as taking the limit of the natural log, because the natural log is a continuous function. So I can actually pull this limit outside of the natural log, as I have here. So this second step is the same as e to the limit as x goes to infinity of the natural log of 1 plus 1 over x all raised to the x power. Now, something nice happens. Since I've now pulled this natural log inside the limit, remember that since I have a natural log and it's raised to an x power, that exponent can be pulled in front of the natural log. And that's true of all logs, but we have a natural one here. So this is e to the limit as x goes to infinity of x times the natural log of 1 plus 1 over x. Now let's think about this for a second. Let's plug in infinity and see if we have indeterminate form. X is just infinity, and this function, 1 plus 1 over infinity is 1, and the natural log of 1 is 0. So we technically have something in the form of infinity times 0. That is an implicit indeterminate form, but remember, infinity times 0 or negative infinity times 0 can be rewritten as either infinity over infinity or 0 times 0. This is indeterminate form. I just need to flip one of the terms into a denominator. So here I have what we originally had. E to the limit as x goes to infinity of x times the natural log of 1 plus 1 over x. What I'm going to do to get this in explicit indeterminate form is I'm going to pull this x into the denominator of the limit. And the way I do that is I make the limit as x goes to infinity of natural log of 1 plus 1 over x divided by 1 over x, or x to the negative first power. And the reason I put it as x to the minus first power is now I have explicitly in a way that's easy to do power rule. Okay? And it's e to everything. Alright, now I'm going to apply L'Hopital's rule, which is good for 0 over 0 or infinity over infinity. Let's take the derivative of the numerator. It becomes 1 over all this, 1 plus 1 over x, and then I need to take the derivative of the inside function, 1 plus 1 over x. Well, that's essentially 1 plus x to the minus first, and so the derivative would be negative x to the minus second, or negative 1 over x squared. Alright? In the denominator, the x to the minus first, if we take its derivative with respect to x, it just becomes negative 1 over x squared. Also, notice that these negative signs are in both the numerator and denominator. They will essentially cancel, okay? But I'll do that in a minute. What I need to do first is actually multiply both the numerator and denominator by x squared. So multiplying by x squared over x squared, that's like your fancy 1. It doesn't change the value of the limit. So this x squared times 1 over x squared goes away. In the denominator, the same thing. X squared divided by x squared, they go away. And the negative signs cancel, and so all you're left with is e to the limit as x goes to infinity of 1 over 1 plus 1 over x. Now the question is, can we evaluate this limit? Yes, it is no longer an indeterminate form, and that's a good hint because the numerator is not a 0 or infinity, all right? So if we plug in infinity essentially for this, the denominator becomes 1 plus 1 over infinity, or 1 plus 0. And so this limit is e to the 1 over 1 plus 0, or e to the 1 over 1, or e. And therefore, we have just shown that the definition of e, which is this original limit right here, is in fact e. Okay? So kind of a nice fancy application of L'Hopital's rule, where we started with one of the non-traditional kinds of indeterminate form, where we have something that's in the form 1 to the infinity, and then we ultimately broke it down and saw that its value was in fact e. Okay? So, hopefully these past few videos have given you a good grasp of using L'Hopital's rule. And I tried to use some pretty difficult examples so you get a good understanding of this. Please make sure to like this video and subscribe to the channel for future videos and notifications. Thank you very much.